All right, let's dive into something that sounds like it's been pulled straight from a sci-fi novel, but it's based on some seriously groundbreaking research. It's time to pretty much rethink everything you thought you knew about quantum computing, because we're looking at a completely new kind of machine. So, just for a second, forget about silicon chips and those supercooled wires. What if the real key, the thing that unlocks the next generation of computing, wasn't in some vacuum chamber at absolute zero, but was actually swirling around inside a chamber filled with water and light? It's a wild idea, I know, but we're about to see exactly how it might work. But first, to really get why this new approach is so revolutionary, you gotta understand the huge challenge that every single quantum computer today is up against. They're unbelievably powerful, yeah, but they are also incredibly fragile. Think of today's quantum machines like these world-class sprinters who can only run inside a perfectly controlled, totally sterile bubble. The potential is immense, for sure, but the conditions they need to operate in are just a massive hurdle. This new idea, though, suggests a totally different path, one that actually works with nature instead of fighting against it. And when we say extreme conditions, how extreme are we talking? Well, we're talking about temperatures colder than deep space. In a perfect vacuum, where a single stray vibration or particle of heat can completely wreck a calculation. This right here is the central problem. Building these things, and especially scaling them up, is just astronomically difficult and expensive. So, how do you solve a problem like that? Well, this new architecture doesn't just bend the rules, it throws the entire rulebook out the window. It proposes building a computer from two of the most basic, fundamental things in our universe: water and light. And here it is. It's called the Hydro-Photonic Quantum Computer, or HPQC for short. And the name really tells you everything. Hydro for water and photonic for light. Instead of those sterile vacuums, this is a system that does its quantum magic inside a fluid, right at room temperature. It uses a network of nanowires and layered disks to sort of guide and shape that light, creating something totally new. This is a complete reimagining of what a quantum computer even is. Now, to truly get your head around how different this is, we need to look at the most basic building block of it all. You know, in our regular computers, it's the bit. In traditional quantum computers, it's the qubit. But in the HQQC, it's something else entirely. So first, just a quick refresher. The qubit is the hero of modern quantum computing. The easiest way to think about it is like a light switch that can be on or off, or somehow both at the exact same time. This superposition is what gives these computers all their power. But, and this is the key, it's still a binary two-level system, on or off. The HPQC doesn't use qubits at all. It uses something called a mum wire. Now, a mum wire isn't a simple on-off switch. No way. Instead, I want you to picture dropping a pebble into a calm pond and just watching that intricate, evolving pattern of ripples spread out. That is basically a mum wire. A continuous, multidimensional field of resonance that's created by light moving through water. And the difference here is, well, it's profound. A qubit is binary and discrete. It's either one state or the other, or a mix. A majere, on the other hand, is this entire evolving, multidimensional pattern. And here's the most mind-bending part. A qubit has to be perfectly isolated from any outside noise. A majere? It actually uses the fluid dynamics, the little bits of turbulence and tiny variations in the water, as part of its calculation. So how is that even possible? Well, the source material calls this concept Megasfinity, and the idea behind it is actually pretty simple. Between any two numbers, say 0 and 1, there's an infinite number of values in between, right? 0.1, 0.11, 0.111, forever. The HPQC uses this infinite continuum to encode its information, and that's what gives a single Mahari its incredible power, an almost unimaginably huge space to work in, way, way beyond the simple binary limits of a qubit. Okay, so we've got water, we've got light, and we've got these multidimensional maras. But how does it all come together to actually, compute something? Let's take a look inside the engine. The whole process kicks off when lasers inject photons, particles of light, into a chamber filled with water. As that light moves through, it gets bent and scattered by a special stack of disks and guided by a network of nanowires. This is what creates that incredibly complex interference pattern we call the myria. Then, a whole array of sensors reads this constantly evolving pattern and, this part is absolutely crucial, a powerful external AI is needed to take all of that complex optical data and decode it into a result we can actually understand. The computation isn't happening in just one place. It's the entire system, the light, the water, and the AI all working together. So yeah, this isn't just some small improvement or a minor upgrade. We're talking about a completely different philosophy of computation. And with it comes some pretty staggering advantages. These advantages are absolute game changers. I mean, imagine a quantum computer that can actually sit on a desk, like the one we see here. Because it works at room temperature, it totally changes the cost and who can access this kind of power. It's designed from the ground up to be scalable and robust. And maybe the most powerful feature of all, massive parallelism. The entire field of water and light is computing all at once, simultaneously. This quote from the source paper really just says it all, doesn't it? It says, "The HPQC embraces the natural fluidic variability of its environment, transforming it into functional computational resources." Think about that for a second. Traditional quantum computers spend billions trying to create a perfectly silent, perfectly still environment. The HPQC does the exact opposite. It takes the noise, the natural turbulence in the water, and makes it part of the calculation. It turns a massive weakness into a core strength. So, when you have an entirely new type of computer, it opens up entirely new possibilities. What kind of problems could we finally solve if a machine like this actually becomes a reality? Well, since the HPQC is itself a fluidic, dynamic system, it's kind of perfectly suited to model other complex systems in the real world. Everything from weather patterns to how proteins fold for drug discovery. Its ability to handle these huge, messy data sets makes it ideal for optimization problems, like in logistics or financial markets. The list of potential applications is it's huge. And that brings us right back to where we started. For decades now, we've thought of computing as this dry, sterile, solid-state thing. But maybe, just maybe, the next great leap forward is going to come from embracing the complex, dynamic, and fluid nature of the world all around us. Maybe the future of computing is wet.